Okay, let me tell you the following. So then I am running for material to introduce himself, and he sent me these few lines that is sufficient for. So then I asked ChatGPT to expand on it, and ChatGPT converted it into different sentences. So then I will not read all that, but I will read the conclusions of ChatGPT and the introduction. So then you ask Roni Harnik got his PhD in theoretical particle physics from UC Berkeley in the year 2005. He was a postdoc at SLAC and Stanford before joining Fermilab in 2010. Roni is the head of the Fermilab Quantum Theory Department and is the science trust lead of the SQMS Quantum Center. And if you wonder what SQMS is here, Superconducting Quantum Materials and Systems. Yeah. So he's also a member of the Aspen Center for Physics. And he works on physics you understand a lot and ways to explore. ChatGPT wrote a lot of things beyond, but I will tell you from everything and read the conclusions. Roni Harnik's career exemplified the spirit of scientific exploration and collaboration that defined the forefront of particle physics research. From his foundational work at UC Berkeley to his leadership at Fermilab and beyond, Harnik continues to shape the landscape of theoretical and experimental physics. His contributions not only deepen our understanding of the universe, but also inspire future generations to push the boundaries of scientific inquiry. As he continues to innovate and lead at the intersection of theory and experiment, Roni Harnik stands as a beacon of scientific achievement and discovery in the field of particle physics.
Oh, wow.
Further words, Roni.
Thank you. Thank you. Carlos, wasn't the number 3 or 4? That's no. ChatGPT said nothing about my wonderful supporting wife. So, and yeah. Okay. Can you hear me?
Yeah.
Yes. Okay. Thank you very much, Carlos, and to artificial intelligence for making up this introduction. I will tell you about quantum devices for high-energy physics, or maybe it's for high-energy physicists, and vice versa. So it's more, yeah, you'll see what the talk is. The title doesn't quite do it justice. I'm from Fermilab, which is near Chicago, and we're the high-energy. Okay, so this is an Aspen Colloquium. The goal of the Aspen Colloquium is to speak to all of the participants of workshops and others that are at the center. So here are the workshops that are ongoing. Let's see if I can get the. So the workshop that I'm part of, so I'm part of the team Neutrino. Neutrino is a lepton. So this is leveraging the lepton sector as a probe for deep physics. That's ongoing, and welcome to Aspen, to the new kids on the block, probing collective excitations in quantum matter by transport and ghost electron. Oh, thank you. And spectroscopy. Keep me honest. Yeah, I'm not supposed to cross this line, otherwise something can get big. Here, thanks. So what the goal for me for today is to tell the condensed matter folks a little bit about the high-energy physics and the topic of this workshop. So I think that would be traditional in Aspen Colloquium. So I'll do that. But this talk is not quite only about probing using the lepton sector. It's about the interface with quantum information science. So it's a little bit out of left field. So I'll tell particle physicists a little bit about the connections of our field to QIS, quantum information science, and how we should embrace it and enjoy it. And I'll tell everybody about, again, the interface between these two fields and In a few places, I'll point out connections to this community, to the condensed matter people, and hopefully I'll also keep you somewhat entertained. Okay, so so the first order of business is to tell you a little bit about particle physics and the lepton sector. So I'm sure you've seen this in many colloquia. We have a fantastic model that describes the universe. It's two standard models, really. Standard model of particle physics, which tells us what the menu of particles and interactions are, and a model of cosmology that tells us roughly what the energy budget and history of the universe. So this is a very nice, successful, and complete model or models. And it comes with a whole lot of mysteries. Many unanswered questions. For example, the stuff we're made of is here, but there's 3 copies of that stuff. Why is that? There are these neutrinos that are very light particles that barely interact with anything. And there's some interesting dynamics between the 3 copies of neutrinos. The weak interaction sector, including the Higgs bosons, comes with its own set of mysteries. What sets the scale for these particles? The strong force, gravity, each has their own set of unknowns. And of course, cosmology is full of unanswered questions. Just look at the name dark matter and dark energy, and you understand that there's a whole lot that we don't know. Also, why there's matter and more matter than antimatter. So there's a whole lot of mystery, and that implies that there's more to this. There is BSM, beyond the standard model. That's sort of, if you ask me in the street, what did I do for a living? I do BSM. So that's, so there are more fields, presumably, to add to this menu, and we will get back to them later. Okay, so leptons, the workshop is, so what are we talking about in the patio twice a week and in our offices when we go hiking together? What do we discuss? Well, we are discussing the lepton. First of all, the leptons are these sets of particles. So it's the electron and its cousin, the muons and the tau, as well as the electron neutrino and its counterparts. These are the leptons, and there's a whole set of very impressive and ambitious, some planned, some ongoing experiments. For example, the most precisely measured quantity in physics comes from measuring the G-2, the magnetic moment of the electron. You take a single electron, put it in a trap. That's a small scale experiment. Measuring the same thing for the muon takes a particle physics experiment. There are dark matter searches that we've been discussing. We had a nice talk this morning about the muon collider that hopefully we'll build someday. There is a very large and ongoing program at Fermilab exploring neutrino physics, the violation of flavors, converting muons to electrons. So there's a lot of experimental activity and a lot of opportunities to learn new things about the universe. So that's our workshop. And again, I'm taking a sharp turn either left or right and telling you about something slightly different, which is other ways to explore nature, which involves quantum information science and quantum devices, which is a new field which I'm sure you all have heard of, and I will try to pitch it to you in my own peculiar way. So quantum information science is emerging because we humans are now able to control the quantum state of all sorts of interesting systems in a way that we could not do before. So this is challenging because quantum states at the microscopic level are very fragile. Yet in labs across the world, people are able to do it. And this goes from superconducting devices. So this is what superconducting qubits look like, cavities, ion traps, interferometers of atoms, optomechanical devices. So all of these are devices. And then there's the question of how do you, if I can process information in a quantum way now, how would I go about it? And that is a field called quantum algorithms. So this package together is called quantum information science. We are going to process information in a quantum way. Very nice. So the takeaways from this talk about the interface of energy physics and quantum and QIS is that HEP, QIS, and also condensed matter, of course, share a common foundation, which is quantum field theory. So I'll talk in a little bit about that language that we use. And these fields are not as distant as we sometimes make them out to be. And of course, we have new opportunities to explore fundamental physics with this technology. And this is a very interdisciplinary endeavor. So ever since going into this sort of field, I've been interacting with many more IB physicists. Okay, so the plan is I'll talk a little because there's a little bit of a cultural divide between these fields, and culture is all about language. So I'll try to talk about one field in the language that another field would be using. So I'll talk a little bit about quantum devices, but I'll use jargon that high-energy physicists tend to use about their theories, which is low-energy effective field theory. And I'll give you some examples of devices in this language. Then I'll talk about beyond the standard model of physics, a couple of beyond the standard model of physics models that we want to look for, but I'll talk about it in a way that maybe a QIS person and hopefully condensed matter folks will feel more comfortable with. And then I'll give you some examples for looking for such models with devices. So you see there are a lot of examples here. So there's a bit of a laundry listy feel to this, but the message you can take away from this is that this is a very diverse field with many little niches and open questions, and we're working on many aspects of it. Okay, so that's what's ahead. Okay, so back to, so I'm going to talk about devices in a way that that maybe IG physicists would find pleasing. So again, IG physicists are pleased when you first show them this picture. They feel smart because they understand everything. And when we show this picture, what we tend to not tell people is that each of these particles is a field, right? It is represented by quantum field, which, if you think about it, is a profound statement by itself. There's a field defined in the whole damn universe just to describe a particle here. That's a wonderful thing. And this field theory that doesn't sound very quantum because this is just a function that contains all frequencies. It's a continuum, right? Doesn't feel too quantum yet. It's a quantum field because this field is not really a function, it's an operator. So if I want to create a state, I can act with an operator on the vacuum and create it. So the way in which we do quantum field theory, at the heart of it is a mode expansion, right? So if we open our favorite, and when I say our IG physicist's favorite quantum field theory textbook, somewhere in chapter 1 or 2, there will be this definition of the field, which is just the Fourier expansion. I give you a function, you Fourier expand it in your head automatically, right? So this is just a Fourier expansion of the field. It's an integral over frequencies, over actually momenta. What the quantum nature of this is, of course, is that we promote the coefficients of the Fourier expansion into operators, A and A dagger, annihilation and creation operators that satisfy the commutation relations in the usual way. Very good. So we're all very happy and familiar. Sometimes when we teach this to undergrads or grad students, we call this sometimes second quantization. For us, this is the first, maybe the only quantization. But that's just a minute. Very good. Lines here. Good. Okay, so now there's this big universe. It's an infinite universe, and there are these fields defined with all frequencies. And now I build a lab, and I construct some thingies in the lab that enforce some boundary conditions on these fields, such that now they must satisfy. They perhaps must vanish somewhere or die off as we go to infinity. So perhaps I put a particle in a box. Maybe I just have an atom sitting in my lab. So now some of the, just because of how differential equations work, some of these modes are taken away from the continuum and are now part of a discretum. Okay, there are a few modes. So are you stretching or raising your hand?
I raised my hand. Sorry, what's U?
U. U is, thank you. Is a, think of it as e to the IKS. Okay, so this is, so usually what we do so before we did this, as particle physicists, so what is the basis? I even said this somewhere. We get to choose the basis in which we expand the modes. And as particle physicists, it's very convenient to work with just plane waves, right? So, so U is just the spatial part of the plane wave, but now I'm giving myself the freedom because I built a lab here, which
The electromagnetic?
I'm being extremely vague. This is any generic field. So I've brought some indices. This could have been an electromagnetic wave. It could be the Higgs boson, could be the axion. I'm being very glib and generic for colloquium's sake. But because I violated, I'm now violating translation invariance. I better pick, sometimes I need to pick a different basis than a plain word. So that's what you use. Whatever I wanted.
Yeah.
Good. So now I pick the basis that fits my lab. And there are some modes that are taken away from the continuum and they're discrete. And because this is a set of measures 0 compared to all of these, I didn't bother taking these modes away from here, but you actually need to do that. Very nice. So now let's just consider, as particle physicists, we always say these words. Let us consider the low energy effective field theory of blah. So now I'm going to just consider the low energy effective field theory of my device, of the thing that I built in my lab. So now I just threw away the continuum interval, and now I'm looking at the low energy effective field theory that involves this discrete field. And so it is, again, in terms of A's and A daggers, when I will write down the Hamiltonian of this field, the Hamiltonian will be a function of A's and A's daggers. And indeed, when you open QIS papers or textbooks, you'll find boatloads of Hamiltonians in terms of A's and A's daggers. So here's how you get from ING physics to QIS text. Very nice. In these, so there are many types of low energy effective field theories that we enjoy considering. Atoms, NV centers, this electron trap, optics devices, superconducting devices of all types, et cetera, et cetera. So that's ongoing around the world in labs. Now I should pause and say that I'm already being a little bit negligent, because it is not true that quantum mechanics shines only when you place sort of finite boundary conditions that are geometrical. There are situations where even if you consider a universe that's full of something, quantum phenomena just happen. And this has to do with other workshop that's ongoing, right? So there are other phases of matter that can be studied even at infinitum without boundary conditions, and they're very interesting. Superconductors, superfluids, of course, semiconductors, topological insulators, et cetera, So I apologize to the practitioners of this workshop for oversimplifying their work, but I felt like I had to make this clarification for the sake of it, and some of these are even useful for. So some of these are useful for what I'll say later as well. So again, in these low energy effective field theories, there are sometimes it's not a discretum. Maybe there's a continuum, but it is a band. So again, I'm being fast and loose here. But the excitations, the basis which I need to choose in order for my calculations to be under control are these collective excitations, which are in the title of this workshop. Good. So fantastic. So let's give a little bit of give a few examples of low energy effective field theories that live inside quantum devices. I'll start with optics, and I'll take a drink of water before I do so. Wonderful. So optics is the effective field theory of light going through matter. Just to remind you how you get from particle physics to optics. A medium, here's a medium. I drew it beforehand, so I don't need to spend the time. And these are little polarizability, these are little atoms that are polarizable. So these are the little polarizability vectors. And the distance between two atoms is roughly a radius, which is 1 over alpha me. But recall that the wavelength of optical light, because this is light coming from a laser, the laser is coming from an atomic transition, that is 1 over alpha squared me, right? There's a different power of alpha here. That means the wavelength of light is much, much bigger than the distance between these atoms. So light interacts collectively with atoms. So each of these jiggles at the frequency of the light re-radiates, there's interference, and all of this can be captured in a low energy effective field theory. So I don't need to describe all these degrees of freedom. I can integrate this out. There's a low energy effective field theory, and there's this quantity, the index of refraction n, which captures the effect of the material on the light. So k equals n times omega. N can be a function of many things. It's a function of frequency, can be a function of the polarization of the light. It can be a function of the direction in which the light is traveling. And there are materials in optic slabs that do all of the above. Now, of course, in optic slabs, sometimes you just shoot a laser into free space, but in this day and age, one thing that's very popular is to build little structures to guide the light. So this is the waveguide. It's very small, as you can see. And the modes, so the modes that got pulled out of the continuum are these. So here's one mode, here's another mode with the same spatial configuration, but different polarization. So these two can have different index of refraction depending on the material. And these are higher order modes. People from my generation immediately think about Kaluza-Klein modes in extra dimensions, which I find very amusing because we were taught physics. We were thinking about something hypothetical in order to get intuition about something that actually exists, and I find that very comical. And I'm happy that some of you actually enjoyed the skip. Very good. But at the end of the day, the Hamiltonian is just the energy density, E squared plus B squared, which is a sum over modes once you expand E and B in terms of creation and annihilation operators. Maybe use the vector potential. This is just the usual pre-Hamiltonian. So this is linear optics.
There's actually index of refraction.
In here, yes, yes.
Set it equal to 1 as usual.
Yes, except that I would be in this waveguide. So I extend my apologies. This is the level of rigor of equations in this talk. So wonderful, even when they're latex. Okay. Now this is a low energy effective field theory, and every high-energy physicist knows that every low energy effective field theory has a cutoff, and at the cutoff you write down higher dimensional operators. So let's do that. There's a cutoff, and it's captured in this beast called chi, or chi2. And obviously, the operator that involves chi2 has 3 E fields. So that's optics. Optics people for you. I did not choose this notation. But yeah, this is the dimension 6 operator. It is responsible for something called SPDC, spontaneous parametric down conversion, also frequency doubling. Hamiltonians like this live in many in any green laser pointer. I'm colorblind, so I can't tell if this is green or red. But this is again the hiding place. The dimension 8 operator is called 4-wave mixing. That's 4 waves, and it's obviously called type 3. These are tensors that depend on direction, that can have multi-figural structure. Again, as high-energy physicists, we all often go to something called naive dimension analysis. I won't go into the details that allows us to estimate what the natural, typical, generic size of these operators would be. And here we know that this sort of physics is generated at the atomic scale. The scale is roughly the Bohr radius, so we can do naive dimensional analysis just by comparison. So these numbers turn out to be roughly correct for typical materials. Just for comparison, in vacuum, which is where particle physicists are used to living, chi2 is 0, obviously, because Fourier is 0. Charge conjugation. And this is there's a famous light by light operator coming from integrating out the loop of the electron. And you see where there are 5 alphas downstairs here and 2 alphas upstairs here. So this is orders of magnitude more than what we are used to as particle physicists. But remember, Avogadro's numbers is large. Atoms are dense. Very nice. So that's optics. So there was linear optics. Then I remembered, oh yes, there's a cutoff, higher dimensional operators, and then there's nonlinear optics. Let's go to a completely different system. So now the frequencies are going to be much lower, let's say gigahertz. And then I'm just going to think about light, and I'm going to put it, say, in a box. So this is a one-dimensional particle in a box, and this is trivial. What's less trivial is to build real boxes. So these are real boxes, the real cavities for photons. They're made of niobium. And the degree to which we're able to separate this discretum from the continuum is called the quality factor of the cavity, right? So that's how quickly I lose something from inside the cavity. Now, routinely in labs using superconducting technology, we can get quality factors of 10 to the 10. Namely, the photon can stay 10 to the 10 periods inside the box.
Is it what other physical fields like in accelerators?
It's whichever you like. So the reason I'll get to this in
Right. So this is
the next. Okay. Yeah. The next. I believe the next slide or one after I'll get to that. But you can either put 10 to the 25 photons in this, or 1. So and any number in between, obviously, not with great precision, but 1 you can do precise.
Yeah.
Very nice. So we will get to it. Of course, there are equivalent things that are equivalent to cavities, like LC circuits. Here, the collective excitation, if you wish, that we are quantizing are the current and the flux going through this system, and these two are essentially equivalent. Here, the frequency is set by the size. Here, it's set by L and C. And in both cases, again, we get just this usual Hamiltonian. Now, in this Hamiltonian, again, the levels are, what did I do? These levels, this is just the number operator, so the levels are equally spaced, famously, like any harmonic oscillators. And here again, like in the case of nonlinear optics, we can go to the next order of interaction, introduce a UV cutoff, and introduce a nonlinearity, a strong nonlinearity. The way to do that is to put in an element instead of this inductor, put in something that has an inductance that depends, that has the back reaction from the number of quanta in the circuit. This is called this is often a Josephson junction. We don't need to say what that is, but these things exist. And again, so what this means at the level of the Hamiltonian now in terms of A's and A daggers is that there is a higher order term in terms of A and A dagger. What that does to the spectrum, it takes it from an equally spaced spectrum to a non-equally spaced one. Now, generically, this kappa would be equal or smaller than the frequency omega, and what I mean by generically is that if I were to violate this, I would need to fine tune, which is possible because this is now a real system, and now this is another one of these allusions to the cultural quirks of high energy physicists, because we spent a lot of time thinking about fine tuning and naturalness. And here it is in a real system with somebody who actually can turn a knob. And then if you ask them to tune this part to make this really big, they actually complain. So maybe the hierarchy problem that we're worried about is real. Good. What does this do? This allows me, so let's say I wanted to move from this level to that one. In this system, I can send a pulse of light that matches this frequency, and that will induce a transition from here to here, but it will also induce a transition from here to there and from here to there. So I have no control over this system. The fact that this is now anharmonic allows me to address each one of these individually. So this is very important for quantum information science because it allows us to have control. So we now can say that we are going to take some basis. Let's say that the occupation number on this ladder is the way in which we choose to store information. So we're focusing again only on the low energy affected field item. Oh, there you go. Between 0 and 1. And I can prepare a state which has some coefficient alpha times 0 and some coefficient beta times 1. And this is normalized properly. Now I can send pulses onto this device and control it. And the way this is depicted in quantum information science is I take a state and then I do some operation on it. So here I do some rotation. Here I make some operation that depends on this other qubit. So you see these things that look like musical notes all over the place in QIS qubits. Now, instead of this qubit, I could take a system that allows me to not only have an occupation of 0 and 1, but have an occupation of 0 or 1 or 2 photons. And this is now getting back to your question, all the way to some very large number. At some point, I will lose state control. This is known as a qubit because it's a quantum bit of information. This is a qubit. The D is the number that you can go up to. Now, so that is akin to saying I will do quantum information science, but not in binary, but in, say, hexadecimal basis. Maybe that can be more efficient. I'm putting this logo here. So let me tell you, by the way, call this a public service announcement. And this is coming back to the question of accelerators. So in order to build better accelerators, so this is a piece of an accelerator. Inside this wonderful state-of-the-art accelerator are a set of cavities, niobium cavities like this, that are controlled and operated in concert in order to accelerate efficiently electrons or protons that are passing through this beam pipe. This is Yelka, who works on these things. Now, this was just the engineering, the material science of making these has been perfected to the level of 10 to the 10 or 10 to the 11 or more in order to make better accelerators. And when you operate an accelerator, you populate these cavities with many, many, many photons, 10 to the 20 something. However, you don't have to do that. You could instead put just 0 or 1. Now, the fact that this is a high Q device means that if I put a single photon in there, it will live for a long time. So just to compare to state-of-the-art qubits, if I prepare a qubit with this rate, and after a while, and a while is a millisecond, oh, this is a typo. 1 will decay to 0, not 0 will decay to 1. That's the convention of these. And so I will lose the information after this amount of time, and this limits the amount of things I can do with this quantum information.
Are you sure it's millisecond? I thought it's more like 100 microsecond.
The state of the art is millisecond.
Millisecond is the best, yeah.
Millisecond is the best. IBM has tweeted milliseconds. At SQMS, we are at, I believe, Jim, 700, 800? 400?
Yep. Well, the last one I saw was 400.
Yeah, so we're at the millisecond.
40 microseconds, 100 microseconds to 100 just does it. 1 millisecond. But anyway, so somebody...
This is ask me next year, and so because this is recorded, and somebody may... so let's extrapolate. Wonderful. But for a cavity like this, the lifetime of a single photon has been demonstrated for 2 seconds. Okay, so that's a big change. Now, of course, controlling a cavity is different than controlling a qubit. So we're not done. It's not like we're going to throw away all 2D qubits and devices and only use cavities. We still have work to do. But this is part of what SQMS is the center at Fermilab that I and Jim Sols, so co-founder of SQMS, this is what we're trying to do. We're trying to use the know-how and the expertise and the systems that we already have from accelerators to make QIS. Very nice. Public service announcement over. Back to what we want to do with this. So one thing we could do with quantum information science is to process information and to compute and to factorize large numbers into primes and break the internet and all of that wonderful thing, and that gets a lot of press. So we all know here that it's premature to declare to declare this a done deal. There are a few decades ahead of us of hard work. But while there's more practical aspirations are being pursued as scientists, we want to ask the question, what will we do for our science if a device like this, a quantum computer, would exist? One thing, so again, this is another issue like public service announcement, because this is not what this talk is about. But if you would like to simulate some systems in higher G physics, for example, the way in which a jet of particles leaves the collision of the LHC, we can describe it well as say a quark coming out and then a lot of mess happens, and out come pions and protons and neutrons and hadrons. This process of hadronization is something that we are not able to simulate in real time, so to speak. The reason at the heart of it is that there are very rapidly, that calculation is just very, very poorly convergent. There's something called the sign problem that has to do with the fact that quantum mechanics has very rapidly rotating phases. So a quantum computer is more suited to address this. And this is an active field. I have I have colleagues at Fermilab, and some of you have colleagues in labs and universities that are working on the new field, which is if we had a working quantum computer, what is the best way to map some interesting problems for us onto the quantum computer? What are the algorithms? How do we prepare the state? How do we read it out? What do we read out, etc. So this is, if you like, this is an offshoot of lattice quantum field theory for the quantum computing. This is on focus in my comment. What I'm talking about is quantum sensing. And people sometimes try to, especially when there's funding flowing into a field, people try to ask, so how do you define this field? So I don't like defining this field. I'm very, very liberal in this respect. But still, it's nice to capture what do we mean by when we say quantum sensing. Well, these are very sensitive devices, and we can control them and we can read information out of them. So these are obviously, they're sensing their environment very well. So sometimes the environment or some new and feeble effect that I would like to measure would cause the appearance of an occupation in a mode. So I'm just exciting a qubit from 0 to 1. That is quantum sensing. So there are examples of this. The haloscope that searches for axion, for those who know what those words mean. Light shining through all experiments. I'll give you an example in a couple slides. Sometimes we essentially remove a whole set of states from our effective field theory. Another way to say that is we undergo some sort of phase transition. So transition sensors and nanowires essentially are Cooper pair breaking detectors in which superconductivity is broken to normal. And sometimes we do things that are somewhat more sophisticated. We take a quantum system, we prepare a very elaborate state, perhaps an entangled state of devices, and we expose it to the environment, and maybe that particular state is more sensitive to the physics we're after. So then you start drawing pictures that look like these algorithmic pictures, but that actually have to do with sensing. I'll give you, if I have time, I will give you an example. Okay, so that was a long spiel about how I, as a high energy physicist, think about quantum sensors. Very nice. Now let's talk a little bit about the things that we're curious about, that we would like to search for. And again, we'll switch languages a bit, and we'll talk. We'll skip all the strong CP and motivational high energy physics talk, and let's just talk as if we're talking to QIS students. Very nice. So first of all, when you're looking for new physics, the first thing that you need to convince a QIS person is that you're not looking for any field that actually exists. You're going to add something new, and that is a cultural difference. High energy physicists do this all the time, and physicists in other areas don't. So I just find that sometimes in the interactions I have in this new field, some time is spent overcoming this cultural barrier. Good, but I think I'm fine with that. You can buy, everybody's buying that I'm going to add a new field. For concreteness, let's say, because QIS is all about controlling, not all, but a lot of it is about controlling photons. So let's just say that I'm going to add a new field, and it's going to interact with the photon. So the question is it going to interact, is this a linear or a nonlinear theory? In the same sense that we talked about linear and nonlinear optics. Okay, so there are two possibilities. Let's go through them one by one. Let's talk about a linear extension. So if I'm going to mix linearly with the photon, I must have the same quantum numbers as the photon. So I need to be a photon, but I need another name. So we're going to call it dark photon, right? Particle physics, that's how we roll. Here it is. I added another field. It's the dark photon. It looks very much like the photon, only has a trine. And now it mixed linearly with the photon, so I can, because I'm trying to accommodate QMS people, I'm writing down a Hamiltonian, not the Lagrangian. And the Hamiltonian looks like, instead of E squared plus B squared, there's an E dot E prime and a B dot B prime. And as is customary, there are typos here, so there should be parentheses here. All of these together are multiplied by a small number, which is also traditionally called epsilon. Very good. There are some fine print here for this theory. The dark photon, I'm also going to give it a mass. It turns out that if I don't give it a mass, I can just change basis rotate between E and E prime and rotate this thing away. But if there's a mass for the dark photon, I can't do that. So now there's some physical effects to be had. So this is just a very simple extension of the standard model, and just taking something that I already know exists and repeating it. Of course, if we were to discover something like this, we'll discover, we'll learn very profound things, perhaps about the unification of forces. We will ask ourselves whether this is or not the dark matter, how much of the dark matter is it, etc.
Really trying to do like experiment to estimate epsilon.
Do
you have any idea what epsilon is?
The epsilon can be anywhere between 0 and some number that I will not actually be showing the exclusion.
If you knew that, you would not know what that photons are.
Exactly. Well, if I knew that, first of all, I would know that dark photons exist. So I'm doing it's hypothesis testing. I'm making a hypothesis. The hypothesis is that the dark photon exists and that it has this coupling. And I test that hypothesis with my favorite experiment. I probably should have put some exclusion plots on what epsilon could be, but you could imagine that the constraints on epsilon are going to be very, very strong. But of course, on a log scale, there's an infinite amount of space below any small number. So they're very. So I got a thumbs up, but I can proceed. So this is a search. Yes. Now let's talk about a nonlinear extension. This goes by the name of axion. So the dark photon was the unique linear extension. The axion is not unique. It's one of the things that we could do, but it's the most well-motivated one because of theoretical reasons that I will just not go into. So again, there's one U field. It needs to interact non-linearly, so it'll interact with two photons, and interacting with an E dot B makes some theoretical sense. So I'll just posit that this is the hypothesis that we want to test. If I introduce this to the theory, so the dark photon, every time I emit a photon, I have some probability of order epsilon squared for that photon to actually be a dark photon. Here, there's lots more stuff that can happen because this is a more complicated nonlinear theory. So I can turn on a B field, and in the presence of a B field, the E field, or a photon, can mix with an axion. An axion can be absorbed by a photon and upconvert, take away its energy and go to higher frequencies. I can exchange an axion, and that will induce a photon-photon interaction. So it will induce, this is a nonlinearity of QD that I'm introducing. So there are all sorts of things that I can look for. So these are the two models that I have in mind in the last 10 minutes of the talk. I should point out that again, these are particles that I'm positing, and I can search for them in two ways. I can make the hypothesis that these particles exist in the rule book, namely that I can produce them in the lab and perhaps detect them or ensure that I produce them. Or I can say, make a stronger hypothesis and test it, but it's a very interesting hypothesis, that these particles make up the dark matter, which is holding our galaxy gravitationally together. That's a very intriguing possibility. Of course, each of these would be tested in a different way. In one case, I would need to produce a dark photon and detect it. This is sometimes known as light shining through wall. I'll show you a real experiment that does that in a slide or two. Or I can just sit and wait in the lab and wait for a dark matter particle to come into my detector and detect. Very good. I prepared 4 examples. We'll see how many I can get through in the 7 to 8 minutes that I have left. So this is, to start with something very concrete, this is an experiment that was constructed very quickly on particle physics timescales at Fermilab. So here's one of these niobium cavities. It has a frequency of 1.3 gigahertz, about the size of a grapefruit. Here's the other one. This is the emitter cavity. This is the receiver cavity. What this means is this was filled with photons like the accelerator cavities that we know how to fill at Fermilab. And this one was kept quiet. All of this was dumped in liquid helium and a test stand that already exists because we need to test cavities for accelerators. And the fact, and we did not see any excess power in the receiver cavity. If a dark photon existed with a certain, so here's the an exclusion spot with the same epsilon. If a dark photon existed with, say, this epsilon and with this dark photon mass, we would have seen some of the photons that lived here would have converted to dark photons and back to photons in this receiver. These two are, this is like 2 tuning forks that are tuned to exactly the same frequency, and you hit one and the sound waves are transmitted to the other. So here, one of the big challenges is to keep these two at exactly the same frequency to get good reach. Jean-Louis made this plot. He's over there.
That the dark photon should not be stopped by any of the stuff. So it's really
Yes. Well, it interacts with matter only through the its interaction with a photon. That costs you an epsilon.
okay. So borders just robust.
That's right. So yeah.
What's the true vector you have here?
This cavity was I want to say between 10 to the 9 and 10 to the 10. They were measured in the experiment.
You say 1 photon Q is lower than the many photons Q.
Yes, but not by much on a log scale. So it was 5 years ago. It was an open question whether these cavities going from 2 Kelvin to millikelvin, whether they would whether the drop in Q that was observed was going to persist or there will be a plateau. Then my colleague Alex Romanenko and Dave Stutter actually measured it, and it turned out that it plateaued and that the Q is still high and it can be treated and addressed. We associate that to 2-level systems, etc.
This epsilon in units where the ordinary spectrum has a coefficient 1.
This is dimensional, so it's not in units. This is dimensional quantity, but it should be compared to 1. Yeah.
And what you measure is order epsilon square in the experiment.
Epsilon to the 4th, really, because I need to emit and detect.
Epsilon.
Yes, but in a couple slides, if I have time, I'll get to an epsilon square experiment. This is by the way not a quantum experiment because this is at a Kelvin, and Kelvin is really high temperature if you are at gigahertz. But the next iteration will be in a Delft.
The 2 cavities they're isolated from each other, but still has to be done, or they're just spatially at some distance from each other. What goes?
They are this far apart. And something special has to be done. Namely, you turn one on and then you see crosstalk. Then you need to wrap all sorts of stuff on the stairs. You need to wrap all sorts of stuff with aluminum foil to protect it, and to maybe replace this wire with a different wire and things like that. So one of the challenges, which I didn't mention, was to eliminate the crosstalk. But that was successfully done in the run that that you saw the result. Okay, we can also look for axions with cavities, and now we're looking for nonlinear effects. There are hosts of possibilities. I will just highlight again, just because of the fact that, first of all, Jim is here, and we're condensed matter and hydrogen physics sitting together. One thing you could do is just look for the exchange of an axion and look for nonlinear effects in a cavity. The cavity is supposed to be a very, very linear device. And one question that one may ask is, how linear does it, how linearly is it? It's a superconductor. So in superconductivity, there is an effect known as the nonlinear micro effect, and Jim, who's over there, my SQMS colleague, studied this and finds that, in fact, the nonlinearity in the walls of the cavity is actually important, and we need to consider this in the way in which we design these searches. If we want to look for the axion using cavities, we probably still need to do it light shining the wall. You can't just look for nonlinearity in a single cavity. So there's we're having fun together. I think that this will be my last example, just because you asked about epsilon and epsilon squared. This is there are two slides here. This now from the world of optics. Spontaneous parametric down conversion is this effect where a pump photon, a photon in the initial state, could down converts to two other photons. Particle physicists would call this a decay. It's a 1-to-2 process, so it's decay. So it's a photon decaying to two photons, which again, as particle physicists, we're not used to at all. But remember, this is happening in an optical medium with indices of refraction that I can control. In particular, the pump can have a different index refraction than the two final state photons. Conveniently, optics people, I did not invent this name, call these two photons the signal, the one that they measure, and the idler, the one that they don't bother to. They don't bother to because they can infer its presence. Okay? And now there are all sorts of rules for what given the frequency of one and the indices of refraction, what will be the frequencies and the directions of emission of the other photons. Now, because there's an idler here, a photon that its presence can be inferred, I don't need to detect it. Now I can infer of some particle that escaped my detector if I just replace the idler photon with an idler dark photon or an axion. So this goes by the name of dark spontaneous parametric jump conversion. So I worked on this with Fermilab experimental colleagues in the midst of the pandemic. And we proposed this search. So this is actual experimental realizations are in design, but this is a way in which you can emit some new physics and only pay epsilon squared and not pay epsilon to the fourth. Now, it should be said, I'm in front of hydrogen physicists. We do this at the LHC and at colliders all the time. This is known as a monophoton search. But this is now done on the optics state. Good. I have some more examples, but I'm out of time, so I won't tell you about them. Here, this is an example where I have a detector which is n qubits, and I prepare a state and that it would interact with dark matter, but I will not I will prepare the state in such a way that I will not know which qubits it interacted with. So instead of a scaling with n, I'll get a scaling with n squared. That'll be cool. So this is work. This is an idea that's in its infancy from Japanese colleagues, and we're working on similar things. There are opportunities there are uses for dark matter detection for condensed matter systems and novel materials. I'm seeing after. Some of us in this workshop have worked in this theory. Actually, some of them in this workshop have worked in this year. But I'll conclude that the quantum field theory that we have people have been brought up to loving extends into the devices and into the labs of QIS folks. The language that we use has some synergy with the language section things. So there's a growing interface between hydrogen physics, fundamental physics, and QIS, Quantum simulation, and sensing. So just to see what's going to come next. Thanks.
Okay, and you'll invite Yonit.
Please look in, but you see there.
Thanks, Roni. Very nice talk. I was wondering if we go backward from hydrogen physics to quantum information, can we learn something from, we do the entanglement all the time and these factors that build on entanglement. So we know that the linearity basis it can be shown to be satisfied by the factors.
Which duality?
The Bell.
Yeah, Bell inequality. Yes, sir.
Can we infer something quantum information of obvious in space, because we have both space-like and time-like integration, which this happens.
And what it's switching for tau because you wrote a paper left. Okay. So this is a question that people are asking, and I think it's a little bit it's still a bit of a new question. So I'm not sure what the consensus answer is. But I think it is clear that you can do Bell inequality tests in regimes and with particles that have never been used before. Does that mean anything? Is there any reason for us to expect the Bell inequality to be violated in those systems in particular? I'm not aware that there are. But but it's somewhere here. I would defer the question to.
Questions?
Yes.
This is maybe a very stupid question, but in the condensed matter world, we talk about quantum field theories, and many of them are strongly interacting such that you can't write down a gate for that on critical phase straight metals. And so it strikes me that if we find these sort of excitations in condensed matter, perhaps they exist in the universe broadly. How many of these proposals for beyond standard law of physics would be sensitive to such non-particle forms of matter?
We, in our world, we often invoke strongly coupled sectors. And it's not because we're particularly imaginative, it's because we already have strongly coupled sectors. So quantum chromodynamics, QCD, is also a strongly coupled theory for which we have a good high energy description and a good effective low energy description akin to the systems that you have. And then when we go and model build, we often take inspiration from systems that we know and say, okay, let's imagine the dark matter is made out of some protons and neutrons, but it's the dark protons and dark proton. And maybe there are dark atoms. Gordon wrote a paper called Atomic Dark Matter. So so in terms of inventing models, we draw inspiration. Maybe not as much as we should from condensed matter systems, I would say.
Maybe remark in this context. I think that all the physics that you do, you involve always Lorentz invariant. And Lorentz invariant in most matter physics will not give quantum theory. No.
Right. In most of the physics that we do, we invoke Lorentz invariance every time it's not broken. Sometimes it's broken. An experimental, well,
would be lovely.
This is here, and it's not there. So this is breaking Lorentz invariance. Translational.
That's getting like photons there, not a question of gravity.
That's
So
right.
in that sense, the fact that you put it in a cavity is breaking. Is that what you're talking about?
For example, or okay, I think you want something more fundamental that I didn't do. Let's say the dark photon that I just told you about is the dark matter. The dark photon is a vector. It has a direction. So if I probe the dark photon with the cavity, it's pointing in that direction now, and maybe a minute later it'll be the polarization of the dark photon will be pointing elsewhere, and my experiment, which is oriented like so, will give me different results. So rotation invariance is spontaneously broken by the existence of this particular dark matter model. So it just maybe I'm being argumentative, but sometimes we violate Lorentz invariance. That's not a whole. Yeah.
I know there are people who do theories that broke.
Yes.
We last, but I don't know that there are any experiments.
There are experiments. There's a I believe Kostolevsky from Indiana is the father of the rightful owner of the sort of minimal Lorentz invariant standard model. He wrote down systematically Lorentz invariant interactions, and there are many experimental tests, including experiments, atomic experiments of the South Pole by Romualdez, all sorts of good stuff. It doesn't get as much press as it should.
I was curious about the prediction about the dark spontaneous down conversion. So this is something that's predicted for the vacuum, for the fundamental vacuum, or something which is kind of you do in a material like you do usual SPDC.
This will not happen in vacuum.
Not in a vacuum. So it's like another mode that you would expect to happen in lithium niobate, which is a crystal that this is done.
Well, right. So in lithium niobate, if I arrange for the pump index of refraction to be smaller than the signal index of refraction, so that'll tell me how I'm orienting a crystal to some degree. The decay or the down conversion of the pump to signal plus very light particle will now be kinematically accessible. And I'm using Hanji physics. So another way to say it is that the phase matching, now using optics language, the phase matching, this is cut off, but the pump has some index of refraction, the signal has a different index of refraction, and momentum conservation, phase matching, dictate that this triangle must close, and the sum of these frequencies must that's energy conservation, and this k equals omega, which is not n times omega. So the dark photon is an index of refraction of 1, so that changes everything in the phase matching. But if the inequality that I just said is satisfied, this is kinematically accessible, phase matchable.
So you're saying that about detecting using quantum sensors to detect these hypothetical particles, what extent do things like no events, two-level systems, whatever, how can you tell the difference between, oh, I see a new particle versus it's just some what that cause?
Yeah, you need to. So precision science is difficult and long and sometimes thankless task. So we need to find ways to characterize the noise in your system and understand it, and that changes very system by system. In this particular example, I can, again, there are specific predictions for what the frequency of the signal would be in the presence of the dark photon. I can test it by rotating the crystal and then just changing indices of refraction. I can change the pump frequency and if the prediction changes. There are all sorts of handles. And again, this is just me throwing out ideas. This is not an experiment that has been done yet, though we have experimental colleagues that are interested in trying it out. For example, when you're looking for dark matter in a cavity, so ADMX is a famous experiment that is looking for the axion they're scanning frequency by frequency, and they do a lot of consistency checks. They measure their noise. So yeah, experimental science is a science, but also
Okay, coming from epsilon 4 to epsilon 12, it requires probably much more stringent conditions because of coherence, because you're really getting rid of the next epsilon square because you're at present your field. It's a coherent spectroscopy.
well, I mean,
That
Carlos's body language tells me that I should talk to you offline. But there's a whole story that I can tell you, but we don't have time.
I think no, okay. Let's have the two last short question. I think the lady is.
Anything your mathematics can't really be short, but I'll ask the question anyway. Astronomers know that dark matter orbits around in halos around galaxies. Because that places a constraint on the mass of your dark photon. And what is that constraint?
Yes. The mass of the dark photon should be such that the Compton wavelength of the dark photon is less than the size of a dwarf galaxy. Otherwise, that's it. Yeah, that's the constraint. 10 to the minus 22 electron volts, right? Okay. And that's it. It's amazing. So between 10 to the minus 22 and an electron volt, there's a lot of parameters. So there are many experiments that one can think of and do. Actually, so we know a lot about dark matter, but also not a lot of